Hi there, in this teardown I'll be tearing down a Viewsat VS2000 Platinum. It's a satellite receiver which, once again, I got from Valley Village. This was $4.99, and this teardown is going to be a little bit different than the last one. I'm not just going to tear this apart, straight out off the bat. But instead, I'm going to be testing some of the parts on it. Now, this does light up. Usually. Oh yeah, I gotta turn the power on. Okay. So, it shows you the LED display is working. So that's good. I took the screws out again to save time. Let's have a look. Now we've got a nice power supply module here, and they've nicely written the voltages down. I don't know if I can see them from here. The shadow is not so good. But I read 30, 23, 12, G8, 3.3, G, 3.3, G. And that'll be the voltages coming out. I'll measure them in a minute. So keep that intact. It's a nice case when it goes in focus. And yeah, it's got a card reader interface board. And this obviously goes to the screen, which I'll do a reverse engineering of the screen. May even keep it intact. And let's see what we have available on here. Okay, oh, it's an ARM processor, dedicated MPEG-2 decoder type board. Which unfortunately, I don't think I'll be able to reuse that one. Some various regulators around, which is odd because there's no 5-volt line on there, so looks like it's all going to be mostly 3.3 volt logic, LVTTL. Okay, so what I'll do is I'll try and get some measuring done. So I'm going to put it on the. Okay, I'll be right back and see if I can find a way of propping this up. Okay, turn that on. Okay, it's not the most ideal. I don't think you can see the salt screen from here, but okay, I'm going to probe the one that says 30. Yep. This says 23, 12. Another G, and does it say 8? Yeah, 3.3, another G, and I'll skip that, and then another 3.3. So the voltages are pretty consistent, and what I'm also going to do is I'm going to quickly probe voltages on the screen connector to see what voltage it's used for the screen, because usually they use 3.3 on those. Okay. 3.3 signal. I got a 5-volt signal there. There must be a 5-volt regulator on the board. I will check that out soon. I'm going to start taking the boards out and have a look. Okay, I turned it off and disconnected it from the mains. Okay, so let's do it. I left a couple of screws and just hold it in place. Okay, the card reader is connected with a ribbon cable, so I pull that out. First screw out. Maybe I should have disconnected the cables before doing that, but well. Okay, so the screen connected off. Power supply connection off. I'm not taking the power board out. I'm not going to do anything with the power board other than, I'm not going to tear it down. That's what I mean. So I'm going to leave it intact. It's more used to me intact than it is in parts. I may keep the screen board intact if it's usable. I'm assuming there's a serial to parallel type TTL chip on here. And the fact that I saw 5 volts voltages, that's promising. Means I can probably directly control it with a pick. Okay. Yep, so there's the Epic 2 decoder chip, it's an ARM, and there's some flash, and some DRAM by the looks of it, so just DRAM. Let's have a look, see if we can get any chip numbers on here. LM358. Oh, nice, an op amp. That is a CS4340. If I'm not mistaken, that is a DAC. I'm assuming it'll be a dual DAC for the audio, because it's only stereo on here. That chip says Hall on it. I don't know. Just Hall on the code. 0521. Maybe that's 21st week of 2005. And this chip here on the right is an EEPROM. 16 kilobits, I would assume. Maybe an I2C, I'm not sure, but 16 kilobits. Anything else interesting on here? ILX 232, I'd say that's a RS232 level translator. And look, see these regulator type chips. Tip 42. This looks like a normal bipolar transistor. Now this one here. Very good view. KA317. That's an LM317 type. And this here is AZ1117, and it's an adjustable regulator. That's probably creating the 5 volts. Actually, if we look carefully, we actually have another one right down there. S1117500. Maybe that's a fixed 5 volt regulator, I'm not really sure. But we have a few nice bits to work with on here. Some nice connectors, a modulator which I really have no use for because I don't have a TV. An optical output. Yeah. An LMB interface. Alright, other side. Let's look at the card reader. TDA 8004. Some kind of smart card control system. Oh no, look at that. A little last minute fix. Looks like 103. It's a 1K, 10K pull up resistor by the looks of it, or pull down, depends on That's a ground plane over a power plane. And okay, now we have the screen itself, the screen board. Some nice buttons on there. 5 of them. And all these, another 7.4s. Come on, 7.4 HC595. Those are serial to parallel shift registers. Yep, 2 of them. And I bet they're daisy chained. So one goes into the other. And this is not the first type of board I've had from one of these. I've taken apart another satellite receiver before. I got this one, and I've reverse engineered it. It looks pretty much the same, except it's a little extras. Unfortunately, the buttons I found are multiplexed, which I don't like. Basically it will multiplex. It'll shift in like a 1 or a 0 from one side of the button, and then read it all off. And that way it checks each button in turn. Now we've also got an infrared receiver here, so we'll have some fun experiment with that. Okay, now what I've done is I've actually I kept the board off the front panel, and what I've done is I've actually soldered wires to the lines that go onto the main board. Now I've reverse engineered the wiring of this board. I'm pretty much figured out how these are connected yet. These are daisy chained, as I thought. That creates basically a serial to 16-bit parallel buffer. And what I'm going to show now is basically the signals in it. Now I'm using an open bench logic sniffer, which I got from I can't remember where I bought it from. It was like Seed Studios or something. I'll put a link below to buy it. And it was about $50 I paid for it. Not a bad piece of equipment, although the software was a bit of a bitch to get going. But you know, once you get it working, it's fine. And a tip for you using it: ground the unused inputs, otherwise you get weird extra signals on your lines that don't make any sense, which I've done with this custom cable, custom header. Can't really see it in there, but I'm only using 5 inputs, but I've grounded the other ones, the other 3. Okay, so basically I have I'm running one called Jawis, I think it's called. That's what it. It's the one I'm running, Logic Sniffer, and hopefully I'll try and remember to put a link to that in it. And this one seems to work pretty well for me. It's another JavaScript based one. And okay, now what you're seeing on the screen is a capture I did earlier. And I don't know how well that's going to show up, but it says 9059. Yeah, I think that's pretty good. And what it is, I captured the waveforms. Now, and I've also decoded it, which I'll be showing as slides on this video. Now, this bit at the beginning here, I figured out is actually a blanking, a packet of blanking, because there's 16 Okay, I'll start again. That's a blanking pulse. Basically, these chips are clock on the transition from low to high. So this is the clock here, and it's strange. It stays high, and then so therefore that's the first clock, and then that's the last clock pulse. And that is equal to 16 pulses. So, and like I said, it's a two 8-bit shift registers daisy-chained together is 16. So, and what I worked out is the first 4 bits, or the highest 4 bits, depending on which way you look at it, the first clocked in. So bit 15, 14, 13 and 12 select whether it's segment 1, 2, 3 or 4. And then the next 4 pulses are not used, which I could probably stick another display on it and have another 4 digits. And then the next 8 digits control all 7 segments of the display and the decimal point. And I've actually mapped it as A, B, C, D, F, G decimal point, all the way from right to left. And it's a common anode display, so basically low pulses in the data line up here means the segment's on, and high pulses mean the segment's off. But over here, there's a display select, how high pulse selects the display. So as you can see, this is actually selecting the first display, and I decoded this to first display, and I decoded this to be displaying a 9. And let's see, if I scroll this along, I'll find another pulse. There we go. See, only the first one has a blanking pulse. This one doesn't. And yeah, this one I believe it was a this was another 9. It's 1, 2, 3. For some reason, it did the last digit first. The first digit, last digit, and I think it did the second, then the third digit, in that order. And I've seen that several times. It was very confusing. If I remember, I'll put a link in the description to so you can download a copy of this project file if you want to open it in the Logic Sniffer software, which you can download and run without having a Logic Sniffer. But yeah, that works pretty good. So here's the configuration I worked out. This is in reference to this. Basically, so it's ground, 5 volts, infrared in, then no connection. It looks like it goes. The no connections go to something that was here. I think it's well, it's a D17, so I think it's some kind of photodiode or something. I'm not really sure. Maybe even a bicolor. I'm not sure. Then you got the button input, which I'm still doing more research on the buttons. From what I've reverse engineered, it doesn't seem to make sense from the signals I'm receiving. I'm working on that. I'm not really interested in that, but I'm still working on it. We've got the data coming in, then the shift and the storage clock. Now, so you understand the so you can see the labels as well. Basically, the shift clock shifts the bits into the register, but nothing comes out in the outputs until the storage clock pulses. Outputs only available in the outputs when the storage clock is high. So basically, it shifts it in, then display, and then it waits again. And yeah, I have worked out the pulse lengths and the frequency of the updating. I will I'll give that information in a minute because I don't have it at hand. I've written it down somewhere and I can't find it right this second. But yeah, so this is the basically reverse engineering of the display. I'll give more information following this. What we have here is a rough schematic of what I've reverse engineered of the screen. On the left you have the input connector which I wired to, and then you basically have the two shift registers in the top middle, some transistors and the LED display. Now keep in mind that this schematic is actually omitting all resistors, capacitors and anything else that's there, and I also haven't put the infrared receiver in it, or the buttons and the diodes. I will eventually do that another time. Right now we're just concentrating on the actual screen display itself. But as you can see, there's a bunch of NPN transistors used to control the common anode for each of the displays, so you can select them in sequence, and this allows digit 1, 2, 3 and 4 to be selected, and then the shift register connects to the segments itself.